So in this video, I want to answer this question. I want us to think about the question of how do we measure the kinetic energy of the electrons? Because we've been talking about that a lot, but how do you actually measure the kinetic energy of an electron? I mean, traditionally we're used to thinking of kinetic energy as half mv squared. That doesn't really cut it in this scenario, okay? We need to use a more sophisticated way to measure it. So look what we've got. I've got some stills here, just some screenshots from that PhET simulation. I'll show you the link in the Google Classroom. It's really, really good, that simulation. I really recommend you have a good look at that. Now, look what's going on in this one here. We've got light of a certain intensity, which you can see there, and it's got a certain wavelength of so many nanometers. And as it shines on the surface of the metal on the left-hand side there, what we can see is, of course, the electrons are being released and they are moving over to here. Now, of course, you can put a cell in here. You can put a battery in there as well. And if you make this positive, okay, so that means this end would also be positive as well, then those electrons are definitely going to go there, aren't they? And the electrons will flow, and that's why we have a current, a flow of charge, a flow of electrons. So when we're measuring the current, we know that electrons are flowing because there is a current there, okay? So that would be in the kind of the usual state of affairs. But look at the second diagram here. Look what's happened, okay? The battery, the cell, has been turned around, okay? So we've turned it around so that it's now facing the other direction, which means that this end is now negative, and so this end is negative and this end is positive. Now look what happens. If this end is now negative, that means that we can draw some negative signs there. This end is negative. It's going to repel those electrons. So those electrons that have been freed and we're moving this way, okay, now they're in the presence of an electric field, the plus and the minus there between the plates, which is going to try and make them go the other way. And what we do is, if you look at the battery here, we can just adjust, okay, the potential, we can adjust the voltage here, and as we adjust it, we can keep turning it, keep increasing it until the current reaches zero. Okay, so what we do is we play around with the voltage here until the current equals zero. So what we can say is we can change the voltage, okay, until the current just stops. So what we've done is we've played around with the voltage, we've made this end negative, okay, and as we've done it, we keep turning the voltage, turning the voltage, turning the voltage until the current just stops. Right, look what we've done, everybody. By the way, we're going to call this particular voltage now, we're going to call this the stopping voltage. In other words, literally the voltage that stopped the photoelectric effect, that stopped those electrons. And it's often given the symbol V small s, the stopping voltage. Well, listen, if you remember, we know that when we've got an electric field, the energy of something, the energy of a charge, the energy that it's got is related to its charge times the potential, or the potential difference between which it moves. So what we do here is we don't measure the kinetic energy of the electrons directly. What we're doing is we measure how much energy is required to stop them, and that would be charge times the stopping potential. That was the energy that was needed to stop them, therefore that is the kinetic energy. So remember when we did the equations a while ago, and we said that the energy going in, so HF, equals the work function plus the kinetic energy. And I also told you that we could write it like this. We could have the work function plus charge of the electron times the stopping voltage. So remember, we don't measure the energy of the electrons directly. We measure how much energy is needed to stop them using what we know about electric fields. We have a potential difference. We know the charge. And when we've just stopped them, we know that the energy we're providing must be equal to the kinetic energy. Therefore, we can say that the E times Vs is going to equal the kinetic